Hello, how are you? Welcome to a new training module in logistics and transportation. This time, we will be focusing on the area of statistical science to improve the competitiveness of freight transport. We will refer to the statistical model that allows us to observe the impact of the factors affecting fuel efficiency. It is evident that freight transportation is one of the key links in the supply chain. Fuel expenses in the freight transport industry can sometimes reach up to 32.5% of the variable cost of any transport company. The theoretical model we present in this session, regardless of many others we will show you, is precisely the one that supports the application of the statistical method to model and subsequently forecast the behavior of an effect of interest, which is what we are looking for and call fuel efficiency. Based on this, several factors, of course, affect the performance you expect. What are the possible factors I am referring to? The weight of the vehicle. For example, the route type, idle speed, whether the driver is driving at an appropriate speed or not, etc. Many variables affect fuel efficiency in a vehicle. To this end, this theoretical statistical formula was created to model the behavior of the unit's fuel efficiency. We will call Y the fuel efficiency of the unit. We will call beta the coefficient of each variable affecting the fuel efficiency of the unit. We will then call X the variable that influences its performance. Therefore, the fuel efficiency of the unit will depend on the fuel efficiency variable itself, plus the variable multiplied by its coefficient, plus the variable affecting the performance or coefficient of the second variable, and so on. Thus, you could have 10 variables and possibly 10 sub-indices that affect it. We will also have the error we are referring to. The model we used for this occasion was based on data from a company that allows us to take consecutive data from different types of units, engine types, and routes. For example, we use T800 engines ProStar engines with differential steps of 4.34 and 4.56, and of course, different engine types. The goal was not to compare whether one engine gives better or worse performance, but rather how the operation influences its performance. Regardless of the age of the unit, for example, our variables for this analysis were route type, vehicle age, and the liters of diesel consumed at idle speed, at low speed. Therefore, there are always discrete and continuous variables in any statistical method or a calculation carried out through different models. We will always call discrete variables those that are counts or enumerations, which can only be recorded with whole numbers. Continuous variables refer to different measures of continuous range of numerical values. Also recorded numerically, the route type will be a discrete variable with two measurements: 0 for kilometers between the origin and destination without slopes or curves, and 1 for kilometers with slopes or curves. The age variable is highly significant in the Mexican fleet. Statistically, it is stated that the average age of the Mexican fleet is over 18 years. Therefore, it is important to always consider it when analyzing performance. Here, we will call it a continuous variable, and of course, the years of service imply a lower fuel efficiency for the unit. The liters consumed at idle speed will be the third variable we call continuous, representing the liters of fuel consumed while the unit is at idle. Continuing with the presentation, we obtained this summary table from several units or many units taken from statistical data. Here, we can see the unit 141, which is 1 year old, had a fuel efficiency of 1.79 in route type 1 and consumed 18 liters of fuel at idle. Of course, fuel efficiency is influenced by many variables, which is why a unit with 1 year of age can have a fuel efficiency of 1.79, while a unit with 5 years of age can have a fuel efficiency of 3.01. If we want to view this graphically, the presentation will look like this. The regression model we present for the entire evaluated fleet is as follows. The overall fuel efficiency of the fleet is 2.093 minus the variable multiplied by its coefficient plus the second variable multiplied by its coefficient and the third variable multiplied by its coefficient. What are those variables? It could be idle speed, vehicle age, or fuel consumption. The model, under optimal levels for the variable stated, indicates that the maximum fuel efficiency is 2.093, and the regression equation shows that this performance is achieved under conditions previously stated. We must emphasize that the regression equation indicates that under certain conditions and variables, the maximum performance for a new unit is 2.093. This graph is very important because it will show us all the units that fell below this reference line and gave a performance much lower than expected, regardless of the variables considered. It can indicate that the way a driver operates the vehicle makes a difference between good or poor fuel efficiency. Here, you can observe that under similar conditions, there are also units that gave higher performance than the minimum expected. A clearer example, using a simpler graph, could be the following. We can observe that the Unit 10 has performance of 1.5, but it has an age of only 1 year. So, the question of whether age affects the fuel efficiency of the unit is answered by saying yes, but not completely. You could compare it with Unit 5, which had a performance of 3. Probably, age does affect fuel efficiency, but the way the driver operates the unit is more significant. If, for example, you could improve just one of the variables we work with, the result would then be different. For instance, instead of 1.54, it could reach 2.54. In this case, this Pareto chart shows how variables A and B had the greatest influence on ensuring that the minimum performance reference line was not exceeded. And these were vehicle age and route type. Of course, we are not considering whether the vehicle was driven at high speed or not, but we are pointing out how these variables can significantly affect fuel efficiency. In terms of correlation, you can see how age can indeed generate a positive impact on fuel efficiency, just as the unit's performance can be affected by the route type, along with many other variables that influence the operation of the vehicle while the driver is driving. Finally, the conclusions based on this proposed model for decision-making using multiplied linear regression on fuel efficiency applied to a transport company are highly significant, as are the explanatory variables such as route type, unit age, diesel consumption, idle speed, etc. The variables explain that when the minimum value, 0, is present, fuel efficiency will be at its highest, which in this case is 2.093 km per liter. This performance factor is much lower than was expected for a new unit, which was 3. Therefore, the company has a lot of work ahead, not only of 3 variables present in this exercise, but on many more that represent the possibilities to improve fuel cost competitiveness. I sincerely hope this video is helpful for raising the competitiveness level of your company. See you soon!